Hello everybody, my name is Ieeevr, and I am one of the authors of this paper entitled A Full Body Motion Calibration and Retargeting for Intuitive Object Manipulation in Immersive Virtual Environments. Unfortunately, due to an emergency, we could not attend the conference this year and the Searis workshop, and therefore I contacted the organizers and the chairs, and I appreciate their willingness to allow us to present this paper over this video presentation format. In this paper, we are proposing a system that combines small finger movements with large-scale body movements that are captured from a motion capture system, and this is basically to utilize this mechanism and in a way that we will be able to integrate the full body motion into an immersive virtual reality application, which I will talk about in terms of the big picture, and show you what we think would be beneficial in terms of integrating these two different types of movements. And by the way, the motion videos that you see here are recorded from a motion capture system, but they don't necessarily have to be from a motion capture system. If you have pre-recorded animations, body animations, skeletal animations that are recorded and pre-recorded, and you have the FBX files, you can actually utilize these animations in this integrated framework. In many virtual reality applications, especially the ones that you want to provide a sense of immersion in your virtual reality environment, full body tracking is a very important task, and it's vital for providing the depth of information to the users, so that users will be able to intuitively operate within this virtual environment while they are completely immersed with and have an immersive experience. What we are considering in terms of extending the tracking mechanisms with this full body integrated framework over the traditional applications is to allow the virtual avatars for our human operators in the virtual environment to be able to intuitively manipulate objects of interest, to have all of the movements, especially the fine-grained finger movements, to be completely natural and intuitive. And at the same time, if you have a situation in which you have a cooperative environment, in which you have you want to be able to have multiple agents, multiple humans in your virtual environment to work with one another, you would like to be able to provide a non-verbal communication mechanisms for the operators, and hand gestures would be an essential component of this mechanism. So this will allow us and would provide us with a higher degree of immersion and interactivity if you compare this with the more traditional virtual reality systems, in which you would have your users to be able to manipulate and work with the environment, but they would effectively become a rigid body, a rigid entity in this environment, and most of the applications are basically happening on a first-person view, so you won't necessarily see their hand movements and the patterns of movements there. And usually, users carry wands or some rigid objects in their hands to basically get a global location for the hand, but you won't necessarily have the finger and gestural information. And so the idea here behind this project is effectively to implement a mechanism that in real time would be able to bridge these two gaps between the large-scale kinematics and the fine-grained finger kinematics. In many virtual reality applications and systems, especially the ones that are designed to bring the users within the virtual environment, both in terms of the physical presence as well as the virtual presence, you might have a mechanism for capturing of the large-scale movement data from the human skeleton. And so, for example, if you think of an application that the users are interacting with a virtual environment in a cave-like environment, then you would have motion capture cameras all around the walls in the cave, and then the users would carry wands and probably put a suit with markers on to track their physical locations, and probably some body part movements as well. And if you have a situation in which you have a head-mounted tracker like an Oculus Rift to immerse the user within the virtual environment, you would be able to track the human head pose with the positional tracking of the head-mounted display. So the idea behind our work is that we would like to be able to integrate this already available mechanism for global movement tracking through HMD positional tracking for the head and user's pose, as well as the full body tracking, or rather the large-scale body tracking, non-rigid body tracking, skeletal tracking with a Vicon motion capture system, or any number of motion capture system for that matter. And then look and see how we can basically add to the layer of interactivity from this system by introducing small-scale motion capture mechanisms for detecting users' hand gestures. So that's basically the idea, bridging these two gaps. And for our particular example, we are using Oculus Rift as the head-mounted devices, and also for or head-mounted displays, and also a Vicon motion capture system for the full body tracking, or rather for the large-scale skeletal tracking, and utilize two different sets of hand and finger movement tracking systems, a pair of VMG30 data gloves, and also leap motion controllers. This mechanism works for both of these systems, and the majority of the results that I'm going to show today is going to be off of the leap motion device. And so at this level, having these mechanisms, it is natural for us to merge these two data together in order to design our system that is capable of tracking both types of the movements. And that's basically the idea behind this project. Okay, before I go into the details of the implementation for this motion integration, let's talk about our platform, and I'm going to discuss the software and hardware choice that we utilize here. So, as I mentioned earlier, for the large-scale motion data, for skeletal body part tracking, we are using a Vicon motion capture system that utilizes 24 T160 cameras, and we use Blade for calibrating and capturing the data from the T160 mocap cameras, and we use Pegasus for streaming this data live into Unreal Engine 4, which is basically our VR engine. And for the finger motion data, as I mentioned, for the particular example of the examples in this presentation, we are using Leap Motion Controller, which is basically very non-intrusive and gives us reasonable data to work with. However, it's quite inaccurate, so we have to actually take care in terms of calibrating and then post-processing the input. For making this motion integration work, we need to include the motion data that is coming in either from an existing pose or is being streamed in from your motion data that is provided by Pegasus from your motion capture system, or from an FBX pre-recorded animation, for example. We need to be able to retarget the data that would match the hand of your virtual character through an IK or an FK chain. One problem with going for an FK chain is that the user's hand is basically, the hand dimensions are ambiguous, and also if you want to go from the upper arm and then utilize an FK change to create or use a one-to-one retargeting for each of the bones orientations, finger bones orientations, this becomes impractical, and so it basically defeats the purpose of having a real-time mechanism that actually works effectively. So what we do is we basically implement or utilize an IK solver that can guarantee that each of the fingers' tip position in the virtual skeleton is basically consistent with the leap motion data that is coming in, and then we kind of sort of go backwards from the virtual effector that we're going to see in a few minutes, that then utilize the forward-backward inverse kinematics to basically retarget the animation.
Before user finger movements can be integrated with the full body animations, there is a need to calibrate the user's hands with the target skeletal hands. This requires collecting the user's finger bone lengths in order to create a mapping between the user's fingers and the corresponding fingers of the virtual skeleton. Next, this calibration data can be used to calculate an effector location for each finger. This effector will be employed in an inverse kinematic solver to find the orientation of each bone within its corresponding finger.
Now, with each of these effector locations calculated and orientation and positions for each finger having been estimated, we basically utilize the effector location in a forward and backwards reaching inverse kinematics, basically, or with the fabric algorithm to find each finger's pose. Once you calculate each of these fingers' poses, then we are using these to cache for the final hand pose. So each of these finger poses will be cached in the animation blueprint for the final hand pose. Then this hand pose will be blended with the streamed Pegasus full body pose, or the full body animation that is pre-recorded in an FBX animation file, and then will be blended on each of the base finger bones to form the final animation pose. Now, before we go to check out a couple of results and see how this system actually works in action, let me emphasize a couple of very important benefits of this platform, especially utilizing Unreal Engine 4 as a base VR environment as well as the animation engine, is on top of the fact that you are able to integrate hand movements directly into full body animation, is the fact that we can actually use the retargeting system to set up an animation blueprint only once for a single skeleton. And once you have this animation set up, or the animation blueprint for a skeleton set up, then we can utilize the retargeting mechanism to effectively, almost intuitively, basically copy the animation from one skeleton and place it on top of another skeleton. Effectively, if you want to think about it, the only thing that the developer will have to do is to go ahead and in their persona, basically, for each of the skeletons they have, to set up the pairing between each main bone, or rather major bone, in both the body and the hand and the fingers of the two animations, basically the target skeleton and the source animation blueprint. And once that is set up, then you can actually retarget the animation and just transfer it from one animated object to another animated object. Also, on top of this, all the data that skeletal, or rather all the skeletal data that needs to be calculated is the effector location. So once you actually calculate the effector location dynamically, you will be able to use this retargeting system to actually implement this mechanism and the blending of these animations on the similar humanoid skeletons as well. And all of this, as I mentioned, is actually happening dynamically in real time. So, I'm going to show you in a couple of slides the results for the skeleton of a humanoid character that looks like, and whose proportions are proportional to the human hands, and then also show you those that are disproportional. Basically, at the bottom here you see examples of this. So on the right we're showing a V pose, or a victory sign on a human hand, where you have the finger lengths and dimensions to be similar to a human hand, and then on the left you see those that are quite dissimilar. So on the left and in the center, these are skeleton structures that do not look quite like a human hand. They may have different fingers, different finger lengths. They may even have different bones within each finger. And so the system actually is capable of resolving these and resolving the issues. Next, I'm going to show you a couple of our results and see how this actually works. Alright, so the first result that I want to show you is taken from a humanoid virtual character whose hands have the same or similar proportions to an actual human hand. So you would have similar number of bones in each finger, and the finger lengths and dimensions are similar to an average human hand. In each of these examples, so I'm showing you 4 different sets of gestures and poses as well in each of the quadrants. So the upper left, the upper right, the bottom left, and the bottom right. And so in each of these images that you see 3 images side by side. Now in each of these quadrants, there are 3 images. The left image is basically the animation without the input from the leap motion. So for example, when the character is idling or when the character is moving about, we are not basically using any hand data, so basically the hand is just a fixed rigid object. The image in the middle is effectively the feeding of the finger animation data from the leap motion directly onto the skeleton, and then without applying the retargeting phase, which was the first phase of this the proposed architecture here, to detect and capture the actual lengths of the fingers and the dimensions of each finger bone, and then utilize that in the calculation of the effector that then is utilized with the forward and backward IK solver to blend the motion into the actual full body kinematics. So the middle image here is the uncalibrated and raw motion data, and as you see, obviously it's quite actually bad. And then the image in the right in each of these quadrants is actually the result of the proposed framework. So as you can see in all of these 4 images, the actual proposed framework actually does a decent job of detecting finger movements and retargeting them and integrating them with the actual motion that is coming in from the alternative large-scale kinematic data from either the motion capture data or an FBX file. So let's break this down and tell you what each of these scenarios do. So the upper left image is basically just you have a flat close hand gesture where you ask the player to actually have their hand relaxed, and it's also showing a T-pose. So we are not using the body animation actually, or the body pose. Then the upper right, we are asking the user to basically do a grasp gesture. So basically as if you are grabbing an object and grasping it. And obviously again, as you see, in the left section you don't have any motion data. In the middle section you're basically feeding the raw leap motion data in, and obviously it messed up the animation there, but the animation on the right image actually shows a decent job in terms of getting the animation in and blending it into the full body. And in this case, the character is also idling. And then the bottom left corner, we ask the player to do a V sign, and then again the left image is no motion data, the middle image is just raw leap motion, and then the right image is the actual retargeted, calibrated and retargeted data onto the full body. And in this case, the character is also walking while they are performing this animation, or there's a walk pattern. And then on the bottom right corner of this image, we ask the character, again in the idling pose, to open their hand. So it's basically an open hand gesture. Then again, in the left image, there is no motion data. In the middle image, there's the raw leap motion data. And then in the right, there is the retargeted and calibrated data. And the base animation here is basically an idle animation. Here, in these results show the same scenarios that I talked about before, but this time we apply this onto a character whose hand dimensions are different than a human hand dimension. And also each of the fingers may have different numbers of bones, different types of bones in them, different bones in them, as opposed to compared to a human hand. The scenarios are the same. The upper left image is basically just a relaxed hand in the idle pose. The upper right image this time is basically that grasp animation that we had, but this time on a T pose. with no body animation coming in. And we have the left bottom image that shows the V sign in an idle case when the character is idling. And so the full body animation here, or the upper body animation here, is basically the idle animation that is blended. And then the bottom right quadrant shows in an A pose, kind of like still relaxed, the character is basically opening their hand or opening their fingers. And as you see, in each of those quadrant images, the rightmost image shows the calibrated and retargeted leap motion data blended into the full body animation, and in all of these cases it's actually doing a decent and a really good job in terms of blending and creating a reasonable gesture.
In this video, the user's hands are already calibrated. We show several hand gestures, including a victory gesture and a fist. We switch from the reference pose to a pre-recorded animation, and the user performs more hand gestures. These gestures include another victory gesture, a thumbs up, and general finger movements. All of these hand gestures are recorded and retargeted in real time using a leap motion controller. For the remainder of this video, the user will perform a few more hand gestures.
To conclude this presentation and the video, we proposed a system that basically combines small-scale movements of a user's finger and hand gestures that are captured with a set of leap motion controllers for the left and right hand, and combines these movements with the large-scale body part movements that are captured from a live stream or from pre-recorded animation data for the large-scale body part movements, and integrates these two different movement patterns into a full body unified motion pattern. The system is quite useful in terms of allowing the users to interact with an environment very intuitively by basically using the full flexibility of their hand gestures and finger movements, as opposed to just using simple interaction and control mechanisms, specifically rigid object manipulation. And also, the system allows for a better level and a higher degree of immersion and interactivity within an immersive virtual reality environment, in that the users will be able to use gesture and hand movements for nonverbal communications or for controlling other entities and other agents within this environment. Now, what we consider as future directions for this research are actually a number of different areas that we could explore. In particular, we are currently looking at, and hopefully would be a very important part of our future work, to build classifiers for detecting more complex interactions and gesture patterns from a user by basically performing two separate tasks. One is to train certain types of gestures and integrate those training mechanisms within our calibration phase that then would be able to learn with the specific user's hand and finger dimensions, as well as their specific way of performing certain gestures, to build these modifiers and then use these modifiers to then, at real time in the live setting, to reconstruct certain types of gestures that users are then performing within the environment. Also, we are looking at utilizing gesture interpreters in a virtual environment to basically connect the user with remotely operated robots. So in this particular case, for example, we are looking at having robots that may share same skeletal structures with the users, such as humanoid robot, or even robots that are completely different or use completely different modes of actions than the users. And then we would want to make a mechanism in such a way that the user would perform an action, such as picking up a rock or opening a door, intuitively as it comes to them, and then learning this pattern of movement and the gestures basically, and translating that onto the remote robots for its purposes of picking up a rock or opening a door or picking up a cargo and things of that nature. So there's a connection that can be exploited now that we have this full body animation integrated that we are looking at and wish to explore further. We would also like to thank our sponsors for this project, the U.S. Army Research Laboratory and the United States Department of Defense, who have provided the support for this project, both in terms of equipment and the research support. Finally, I would like to thank you all for listening to this presentation, and we seek your input in terms of what you feel this project has accomplished and where you see good future directions for this project to be. And if you have any questions, please feel free to email either one of us. I'm Alireza Tavakoli, and my students Brandon Wilson and Matthew Bounds. We work collaboratively on this project, and please feel free to send us your questions through email, and we would be happy to answer. Thank you very much.